This is AQA A-Level Chemistry. We are on part 4 of the haloalkanes topic. We've previously looked at 3 variations on nucleophilic substitution mechanisms. In this video, we're going to focus on the alternative elimination mechanism with OH- acting as a base rather than a nucleophile. As always, I'm going to recommend that you try the activities, pausing the video as you go, and then review and see how you've done. So, as I've already said, the hydroxide ion can act as a nucleophile, but it can also act as a base. And we're going to look at how that looks mechanistically. So if you read through all of this, we can see there's lots of guidance on how you would represent it. And we're going to take a look in a second, but before we do, let's have a look at the mechanism that we have been learning about, nucleophilic substitution. So my OH-, I've got my negative, it's going to attack the delta positive portion of the haloalkane, which is the delta positive carbon. That then means that the CCl bond can't be sustained, so the electrons go from the bond to the chlorine, and we stop, we make our alcohol. But we're now focusing on the elimination. Based on the information on screen now, what would the elimination reaction mechanism look like? Well, we start off in exactly the same way. We've got the OH-, we've got the chloroethane. But this OH- is acting as a base, which means that it's a proton acceptor. When we think proton, we think hydrogen ion. So my arrow, instead of going to the delta positive carbon, goes to an H, but look at where that H is. It's on the carbon adjacent to the carbon the chlorine is bonded to, and that's really important for what happens next, because I've essentially now created a water molecule. That means that the CH bond that we're looking at here cannot exist. Those electrons have to go somewhere, and they actually go from the bond to the CC bond. And as a result, we're creating a double bond there. Now, that then means that we've got 5 bonds around this carbon, which can't be sustained. So the final arrow is from the bond to the chlorine. And we've got the 3 marks there for the elimination mechanism. Now, let's take a look at what we've actually made. And you can see this carbon has gone, this chlorine has gone. So I've got an H and an H, an H and an H, and a double bond has been created. In an elimination mechanism, we go from single bonds to having a double bond because we've eliminated components that were connected to the carbons. And then in addition, we have made water. We can see the water with the H and the OH, and we've got the Cl- ion that's gone off the side. Now, bear in mind, we started with OH- ions. The reagent there would be KOH or NaOH, meaning we've actually made KCl or NaCl. So now a chance to look at a few more examples of these mechanisms. Have a go and then review. So 2-bromopropane and NaOH, remembering that it's the OH- we put in the mechanism. This is going to attack an H. It's on the carbon, neighbouring the carbon that the bromine is connected to. That then means that the double bond is created as the CH bond is lost, curly arrow going in, and then the final curly arrow for the bromine being lost. And that means that in this case, we are making propene, we're making the H2O again, and we're making the Br-, and that Br- will go off to make NaBr, joining up with the Na+ ion that's been a little bit of a spectator. For the next example, have a go if you haven't already. Iodoethane, and so I've got my iodine here. I've got OH- coming in. Once again, it attacks a hydrogen on the adjacent carbon. That then means that the CH bond is lost and those electrons move in, curly arrow from bond to bond, and final curly arrow to show the removal of the iodine, and mechanism done. It's exactly the same format each time. And remember, we've made our alkene, ethene in this case, H2O, I-, and specifically we're making Ki here. And finally, we've got 3-chloropentane and NaOH. So my OH-, it comes in and attacks an H on the carbon adjacent to the carbon the chlorine is on. And I've actually highlighted all of the H's you could do this to. All of those would be equally correct. I've chosen the one that we can see here. And then we've got the bond breaking, so the electron's moving in to create the double bond, and we've got the final arrow showing the removal of the Cl-. And from there, we end up with pent2ene, our H2O, and the chloride ion. So both of these reactions, the elimination we focused on here and the nucleophilic substitution to make the alcohol, they run concurrently. They happen alongside each other. But there are conditions that favour one over the other, and you simply have to remember what's in this table. See what you can remember, and then review. In the first instance, room temperature favours nucleophilic substitution and the formation of alcohol, whereas the formation of an alkene in elimination is favoured by higher temperatures. So you would choose your temperature dependent on which one of those you wanted to be the main product. In terms of nucleophilic substitution, you need to dissolve in aqueous ethanol, whereas for elimination, you dissolve in ethanol. Quite a subtle difference there, and you've got to get them the right way round. And if we think about the type of haloalkane that we start with, primary haloalkanes will favour nucleophilic substitution. Tertiary will favour elimination. Really simple way of thinking about this is more branching means it's more likely that we have elimination. Just in the middle there, we've got secondary haloalkanes that are equally likely to do either. Okay, that takes us to the end of this video, and it takes us to the end of this topic. Thank you for listening, and goodbye.